Today, we're taking a look under the hood, so to speak, at engine design. We're going to explore the theoretical blueprints that engineers use to create the engines that power, well, pretty much everything. So let's just start with the big question, right? How in the world do you even begin to design the perfect engine? How do you turn fuel into motion as efficiently as humanly possible? Well, the problem is that if you look at a real engine while it's running, things get incredibly complicated and fast. You've got friction everywhere, you've got these super complex chemical reactions going on, heat is escaping all over the place. It's just a chaotic, messy system to try and analyze from scratch. So, to cut through all that noise, engineers do something really smart. They don't start with the messy reality, they start with a simplified, perfect version called an ideal cycle. Think of these as the absolute best-case scenario, a perfect blueprint that gives us a target to aim for. So, first up, let's talk about why we idealize these engines by laying out the ground rules for this perfect, theoretical world we're creating. These are what we call the air standard assumptions. It's basically a list of simplifications. First, we pretend the only thing inside the engine is air, and that it behaves like a perfect gas. We also imagine that heat just magically appears from an outside source instead of coming from a messy combustion event. And here's the big one. We assume there's absolutely zero friction and that every single process is perfectly reversible, which is just a fancy way of saying it's 100% efficient with zero energy wasted. It's not real, but it lets us build a clean, understandable model. Okay, so we have the rules for our perfect worlds. Now let's connect all this theory back to the actual physical parts of an engine. Here are the absolute basics you need to know. You've got a piston moving up and down inside a cylinder. The very highest point it reaches is called top dead center, or TDC. The lowest point? That's bottom dead center, BDC. The total distance it travels is the stroke, and the width of the cylinder is called the bore. That's it. Simple enough, right? Now, let's talk about two really important volumes. On the left, you see the displacement volume. That's the huge amount of space the piston sweeps through as it moves from the very bottom to the very top. But look over on the right. Even when the piston is all the way up at TDC, there's still this tiny little bit of space left. That's what we call the clearance volume. And this brings us to what is arguably one of the most critical numbers in all of engine design, the compression ratio. It's just a simple ratio. You take the total volume in the cylinder when the piston is at the bottom, and you divide it by that tiny clearance volume when the piston is at the top. We call it R, and I want you to burn that into your brain because it is the absolute key to understanding engine efficiency. Okay, with all that groundwork laid, let's finally apply these ideas to our first model, the Otto cycle. This is the ideal cycle that describes the gasoline engines in most of the cars on the road today. Now, don't let this chart intimidate you. This is a pressure volume diagram, or PV diagram for short. The easiest way to think about it is as a map, or a story, that shows us exactly what's happening to the pressure and volume of the air inside that cylinder as it goes through one full cycle. Let's walk through it. So we start down at point 1, with the piston at the bottom. From 1 to 2, the piston moves up, compressing the air in that perfectly efficient way we call isentropic. Then, right at point 2, when the piston is at the very top, bam, we add heat instantly. The volume can't change, so the pressure just spikes straight up to point 3. This massive pressure then shoves the piston down from 3 to 4, that's our power stroke, and finally, from 4 back to 1, all the waste heat is instantly ejected, and the whole thing is ready to start over. So what is a big takeaway for the Otto cycle? It is beautifully simple. As this chart shows, the theoretical efficiency is completely tied to that compression ratio, R. The more you squeeze that air, the more work you get out of it. Period. Higher R equals higher efficiency. All right, now for our second ideal engine, the diesel cycle. This is the blueprint for the big, powerful compression ignition engines you find in semis, trains, and massive cargo ships. Now, what's so interesting here is how the diesel's PV diagram is both similar and totally different. The compression and expansion parts look familiar, but check out the heat addition phase, from point 2 to 3. See that? It's not a vertical line anymore. It's a horizontal line. That means heat is added at a constant pressure, not constant volume. So here's how it plays out. From 1 to 2, we get that same perfect compression, but we squeeze the air way more, to a much higher temperature and pressure. At point 2, fuel is injected and it instantly ignites in that superheated air. But instead of an instantaneous explosion, the fuel burns as the piston just starts to move down, which keeps the pressure constant all the way from 2 to 3. Then, from 3 to 4, you get the rest of the power stroke, and 4 back to 1 is our heat rejection. And because of that unique, longer burn process, the diesel cycle gets its own special parameter. It's called the cutoff ratio, or RC. All this really measures is how long that constant pressure heat addition phase lasts. A smaller number means a faster burn. And this brings us to a fascinating trade-off with diesel efficiency. Just like the Otto cycle, a higher compression ratio is a good thing. It makes the engine more efficient. But, and this is the key difference, a longer burn, a higher cutoff ratio actually decreases the efficiency. So for peak performance, you want a diesel engine with a super high compression ratio and a really, really fast burn. Okay, time for the main event. We have our two ideal cycles, Otto and Diesel. If we put them head-to-head in a theoretical cage match, which one is actually more efficient? Well, it turns out the answer is, it depends on the rules of the fight. First, let's imagine a world where we build two engines with the exact same compression ratio, and we put the same amount of heat into both. In this specific scenario, as the diagram shows, the Otto cycle just ends up being more efficient. It converts more of that heat into useful work, so it's the clear winner here. But that's not a very realistic comparison, is it? Real-world engines are limited by how much pressure their parts can physically handle before they break. So what if we change the rules and compare them based on the same peak pressure? Well, in this more realistic scenario, the diesel cycle can get away with a much higher compression ratio to reach that pressure limit. And that advantage lets it squeeze out more work, making the diesel cycle the more efficient engine. So let's just sum it all up. If you're comparing them with the same compression ratio, the Otto cycle wins hands down. Its way of adding heat is just thermodynamically better. But in the real world, where we're limited by the strength of our materials, the diesel cycle wins because it's able to use a much higher compression ratio to do its job. So you see, there's no single best cycle. It all comes down to your engineering constraints. And that leaves us with one final thought to chew on. We've seen the theoretical pros and cons of each cycle on paper, but what are the practical, real-world factors, the things beyond these perfect diagrams, that make diesel engines the absolute undisputed kings of heavy-duty work in our trucks, trains, and ships? That's where the theory truly meets the road.